Well, hello and welcome to our second installment of the Fall 2021 Tennessee Master Beef Producer Program webinar series. My name is Justin Reinhardt. I'm an Extension Beef Cattle Specialist with the University of Tennessee Department of Animal Science. I am the coordinator of the Tennessee Master Beef Producer Program, and myself and Courtney Carter are glad to facilitate these and bring them to you. We are excited about tonight's discussion on genetics and genetic selection, and we'll be answering some questions in the chat and the Q&A box as you put those in here as we get started. But I'll also be going through some of those things that may answer questions as we go along. So let me do that now and just go through some introductory comments on some using the Zoom platform before we introduce our speaker and get started. So the first thing is that I'll mention to you, this is just a test screen examples that we have up here, but you'll see on your Zoom platform that you have a Q&A box. Looks like a couple little quote bubbles down there at the bottom should be on your software platform there. So you'll click that, you'll be able to type in a question. I'll be monitoring those and Courtney will be monitoring those as well as Troy speaks to us this evening. We may answer some of those questions as we go along in text there. And I'll also kind of keep in mind kind of curate those questions to ask to Troy live, just he and I in discussion at the end of his program, or if it's appropriate, we'll stop in the middle of what he's doing and ask some questions so he can address those then. So again, you should see that Q&A bubble at the bottom of your screen. You can click that and type your questions in. We'll either answer those directly in that box, or I'll bring them up with Dr. Rowan at some point in his presentation. You'll also notice that we have interactive questions as we go along. If you were on the first webinar that we had in this series, then you probably were able to see those. They don't show up on every, platform or every user experience interface that is out there, but certainly if you're watching on a desktop through the Zoom desktop software, then you should see this question pop up when Courtney activates those. She'll read the question to you. You can make your choice of the multiple choice selections below the question, then hit submit. And that just gives us a good way to gauge where you are as a group of producers that we're speaking with tonight, and get some feedback on what you experience or how your perspective on certain things so that we can tailor this discussion to that. So again, when Courtney activates these questions, she'll read those. You should be able to click your answer directly in that box as it pops up on your computer or phone, and then we'll be able to, we don't see your individual answer, but we get totals and kind of distributions of the way those are answered. There's also the chat box as well. We'll have some activity in that, and we'll be monitoring it. If you have questions, you can put there. We'd prefer the questions that have to deal with the topic tonight and go in the Q&A. But certainly we'll be looking at both. And if you have some technical questions that we might be able to help with, you can put those in the chat box. That might be the best place to have those. So with that, I'd like to introduce our speaker for this evening, Dr. Troy Rowan. Troy, I just noticed that I might not have changed your title correctly for tonight. I think we're going back to the basics, and this is the one you did in the previous spring webinar series, but talking about back to the basics. So Dr. Rowan is still, we call him new. He's relatively new to the University of Tennessee Animal Science Department, primarily has a research appointment, but he's also an extension specialist with us here. And so when we get questions about genetics, genetic selection, genomics, those kinds of things from producers across the state or even in other states or other countries, we'll direct those to Dr. Rowan, because that's his background, his training. He did his graduate degrees at the University of Missouri, originally from Iowa, and grew up on a Charlet outfit there in Iowa. So we're glad to have Troy. There's two things that Troy knows really, really well, and two areas of kind of subject matter that I ask him questions about and try to get some consultation about as often as I can. One of those is certainly genetics and genomics. I'll put those together. And the other is music. So he's good for answering questions and giving consultation on music selection and genetics and genomics. So with that, Troy, I'll turn it over to you and I'll stop share. I'll let you take over and start your presentation. Thanks for being with us.
Right on. Thanks, Justin, and thanks for pointing out my music recommendations as a strength. I try and curate my music as well as possible. So I'm glad that my tastes are shared elsewhere.
I should maybe add books as well. So he's good for giving book references.
Books and music. Just don't ask me to write or don't ask me to sing, but I sure know how to listen to both of those things. So with that, thanks again, Justin, for the introduction, and Courtney for all the work that you guys do on this Master Beef program. I'm really excited to give this talk tonight that really focuses on back to the basics, right? I think a lot of times we sort of dial in on some of these topics, right? It might be selection indexes, it might be a deep dive into what genomics are, but I think that sometimes it's really helpful to take a step back, look at the big picture, and really start to hone in on some of these core concepts that make everything else that we do in genetics and genomics work. So I'm gonna try and do some back to the basics, but I also want there to be some practical knowledge there. If you're a newer beginning farmer, I really want to lay out some of the things that you'll hear me and others talk about when we're talking about genetics moving forward. But I think that it's really helpful in the context of what genetics are to take a big picture view of genetics, right? And the progress that we've made over a really, really short amount of time in doing genetic selection. And I know this is Master Beef Producers seminar, but I think that this image of the chickens that we're making, these broilers, is very, very powerful, right? From back in 1957, fast forward less than 50 years, the massive amount of genetic progress that the poultry industry has made is immediately apparent. And I think that's sort of where we're headed in the beef industry. Maybe not these giant, big, bulky broilers, but the power of doing selection in a concerted way, especially when we're able to dial in and just focus on genetics, is really, really powerful for our industry. And I think the reason that this is necessary, right, that we have to keep pushing this genetic selection envelope, is that we need to continue to do more with less, right? So this is an image, and I realized that I forgot to plot the colors here, but in the blue we have the nation's cow herd. So this is the number of cows each year from about 1950 all the way up to present day. And in red is the pounds, millions of pounds of beef, right? And what you'll see is that while we're slightly increasing the amount of beef that we're making, the national cow herd it peaked back in about 1975 or so, and has been on a steady decline since then, right? So this is really a testament to a number of things, right? Not just genetics, but things like nutrition, animal health, reproduction, all of these things that we can piece together to do more with less in our cow herd. But I think that as we start to think about feeding a big world food population, whether you have 20 cows or whether you have 2,000 cows, understanding that our margins are getting slimmer, but the world's taste for beef is not going to go away, right? So there's this pressure from the world to do more with less, and I think that a big piece of that is genetics, right? And like I said, there's been a number of things that we've made improvements on since the 1950s, and we're continuing to make improvements on today. Justin will talk more about reproduction. Dr. Katie Mason will talk about nutrition. Dr. Lou talked last time about animal health. Our management practices are getting better. And ultimately, the ability to do genetic selection is done nothing but improve in the last 50 years, right? So we've basically been selecting animals based on what they look like for about the last 10,000 years. And only very recently have we developed tools that allow us to start dialing in just on the genetic component of these animals and do more accurate selection and make genetic progress faster. So I think that genetics is also interesting because it touches each one of these things. Many of these things like animal health or reproduction or an animal's ability to turn pounds of feed into pounds of beef, these are all have a genetic component. So finding ways to dial in and select for those pieces that are genetic can help us answer this call to making more beef with the same or less resources moving forward. So tonight, like I said, I want to do some back to the basics. And I really want to focus in on getting some definitions down, understanding some really core concepts to other things that I'll talk about throughout the talk here. We'll talk quite a bit about doing genetic selection versus phenotypic selection. And I'll get these definitions laid out in a lot more detail as we move forward. For the new and beginning farmers, we'll take a really step-by-step look at EPDs. So what EPDs are, and how they're utilized, so what they look like in practice. We'll also talk about EPD accuracy, and along with EPD accuracy, we'll touch just a very little bit on genomics, and I'm sure you'll hear me talk more about that in future discussions. But this is the roadmap for where we're headed tonight, and I think we're going to go ahead and get started with the poll question right off the bat. So if Courtney wants to pull that up, my question is, do genetics or environment play a bigger part in the expression of phenotypes in cattle? I'll let those give you guys a little bit of time to answer those.
Yeah, I'll tell you when it gets close. Usually 30 seconds is enough.
Okay, that'll work.
About 10 more seconds if you want to answer. All right, sharing with you.
All right, so the poll says 61% of people said that genetics plays a bigger part in the expression of phenotypes in cattle. 12% say the environment, and 27% say it depends on the trait. And so this might have been a trick question. A genetics guy comes up and gets to talk. You'd always think that the answer would be genetics, but hopefully what we'll walk through in these next few slides is that the amount of variation in a phenotype that's controlled by genetics versus the environment is going to really depend on the trait, right? So there are certain things that are very, very highly heritable. So they have big genetic components, and others that aren't. So we'll, like I said, walk through that in some more detail in the next few slides. But before we start talking about heritability, I think it's helpful for us to kind of divide the types of traits or phenotypes. I use trait and phenotype sort of interchangeably in my speaking. So there are really two types of traits, right? One that we call simple, and others that we call complex. And so simple traits are going to be traits that when we look at the genetics that underlie them, they're going to be controlled by one or just a handful of genes, right? So they're simple in the sense that there's only one or two or maybe three different places when we look across all of the animal's DNA that's going to dictate the inheritance of that particular trait. So what that means is that these things are fairly easy to track the inheritance of, right? So when we think about dominant or recessive traits, we think about Mendel's P experiments that he did. That's probably familiar from high school biology classes, or we start to think about some of these other traits that we know the inheritance patterns of really well, in particular in cattle, things like horns or coat color or genetic defects. These are all things that we can interpret as simple traits. They're going to have that really straightforward dominant or recessive inheritance, and we can look back in pedigrees and very easily predict what an animal's phenotype is going to be for these simple traits. But these are really sort of the corner cases of traits that we care about in the beef industry, right? Most all of what we care about are what we call complex traits. So these are going to be traits that are controlled by hundreds or thousands of genes spread all the way throughout the animal's genome. And the genome is the animal's complete set of chromosomes, all of its DNA. And these complex traits are going to have pieces of that DNA spread all the way throughout that are going to control the expression of these traits. And inheritance is going to occur on a continuum, right? So we talk a lot about these bell-shaped curves in genetics, and this is really what these complex traits look like. We have lots of animals that are average. We have a few animals that are intermediate on either side, and just a handful of animals that are extremes on the extreme ends of this phenotypic distribution. And the way that we can start to think about complex traits is resemblance between relatives. And I'll talk about that quite a bit more as we move throughout this presentation. But complex traits, a tall set of parents are going to be more likely to have a tall offspring, right? But there's no guarantees, right? Because again, that offspring could be on this distribution of phenotypes. But when it comes to cattle, the things that we think about and the things that we're trying to breed into our cattle are overwhelmingly going to be complex traits. So things like weaning weight, fertility, calving ease, carcass traits, feed efficiency, all of these traits that we care about in the beef industry for the most part are going to be complex in nature. So lots of different DNA that's playing into the expression of those traits. And so as we start to think about these complex traits, the other way that we can sort of categorize them in the amount that genetics plays into the expression of the trait is through this term called heritability. And the way that I define heritability is the proportion of variability that's controlled by genetics. So what percentage of that phenotype that we're observing is genetics responsible for, right? So the higher that heritability is, the more offspring parent resemblances we're going to see. So for very, very high heritability traits, you can say with pretty good certainty, if you have two parents that show an extreme end of this phenotype, that the offspring is also going to do the same. But for very, very low heritability traits, there's not going to be that very clear parent offspring resemblance oftentimes. And so this leads me into my next question is, which traits do you perceive as having the highest heritability in your herd? So this can just be anecdotal, what you see out in your herd. Which traits that I list here, this is an incomplete listing of traits, do you see the most parent offspring resemblance in?
Sorry, I got distracted.
You good?
Boy, I've got a good scenario already for us. So I think I'll save it to the end, but
Okay.
somebody typed in a question in the form of scenario. I think it'll be a really good discussion point for us, and we'll be able to answer some other good questions from it.
Perfect. That'll work.
Maybe 10 more seconds if you still want to answer. All right, sharing with you, Troy.
All right. So the poll answer here, there's a pretty even split between fertility, weaning weight, and docility at about 10 to 20%. But overwhelmingly, mature size is the one that that most of you answered as being the highest heritability, and that is the correct answer. If we start looking and digging into reported heritabilities at a lot of breed associations, what you'll see is that mature size is very highly heritable. It's heritable in cattle, it's heritable in dogs, it's heritable in humans. If you're a tall cow and you're bred to a tall bull, you're more than likely going to have a tall calf, right? There's not a lot of environment at play in determining things like mature size. So these are things that when we're doing selection, we're making breeding decisions, keeping an eye on mature size is very important, because that can really trickle through your herd, and it's a very highly heritable trait that can last for a really long time moving forward. So good job on the homework there, and I'm going to keep on moving. And I think that it's helpful as we start to think about the genetic component of these traits and heritability is breaking out the phenotypes that we care about into their two components, the two things that play into these phenotypes, one being the genotype of an animal, the other being that animal's environment. And so when we think about this, the high heritability traits that we're seeing, so for things like mature size or frame score, whatever that might be, these are going to have very, very high genotypic contribution. So the animal's genes that they inherit from their parents are going to play a very, very big part in the expression of that phenotype, whereas the animal's environment is going to be less important than for other traits. But for things like fertility, animal health, these are traditionally pretty lowly heritable traits. So that means that the animal's environment is going to play a much stronger part in the expression of that phenotype. But there is still going to be some genetic component to that animal's phenotype. And I think that it's really important to sort of underline that for these really lowly heritable traits, just saying, they're lowly heritable, we can't make genetic progress on them, really defeats the purpose of doing genetic selection. And hopefully I can help everybody understand why that's really important. that for lowly heritable traits, having EPDs and genetic predictions is especially important. It's much more powerful than for very, very highly heritable traits. And I hope I can walk us through that as we move forward here. But just for a little bit of a perspective, I pulled this table from the American Angus Association. These are their most recent heritabilities for all of the traits that they're reporting EPDs on. So I think they're up to something like 24 traits that Angus is reporting EPDs on. So a really, really big suite of traits. And you can see that they span the spectrum of heritabilities from things like heifer pregnancy. So again, that's going to be one of those very lowly heritable fertility traits at about 15%. Things like maternal milk, that's going to be down at about 12%. Whereas for things like mature height, we're all the way up to about 0.6. So 60% of the variation that you'll see in an animal's mature height is going to be controlled by that animal's genetics. So this is just sort of a perspective, a measuring stick, I guess. Some of these traits that we care a lot about, right, in our herds, things like weaning weight. If we're selling calves at weaning, that's sort of the big trait that we're going to be interested in. That's only about 30% heritable, 0.28 heritability. So lots of environment that comes into play, but that doesn't mean that we can't still make genetic progress on these things, even though genetics only makes up a smallish part of the picture there. And the other thing that I'll point out along the same lines of heritabilities is this idea of genetic correlations. And we know that in biology, different genes are going to affect multiple traits, right? So there's not one gene for every trait, unless we're looking at some of those more simple traits. But the tall gene doesn't exist. There's 10,000 genes probably that play into how tall a person or an animal gets. And in addition to dictating how tall an individual gets, those genes are also going to play a part in how heavy an animal gets, how healthy that animal is, how fertile that animal is. So there's genes that are playing parts in a lot of different phenotypes. So that means that for certain traits, you're going to see that if we select for one trait, we're also going to increase another trait, even though we might not be doing selection on it. And that's because of these genetic correlations due to shared genetics that govern the expression of these traits on a genetic level. So for example, things like if we're selecting for increased calf weaning weight, again, we know that that's a trait that we care a lot about if we're selling at weaning, but once we're doing that, we're also going to increase the mature cow weight of our herd. So that's because of these genetic correlations, these shared genetics that are governing these traits. Also things like selection for increased milk. If you have a cow that milks more, that's also going to increase her maintenance requirements. So we have to be careful when we're doing genetic selection that we're balancing these things and accounting for the correlations that pop up here. And here's just some examples of genetic correlations in Angus. These are going to range from 0, which is completely uncorrelated, to 1, which is a perfect correlation, which means that there's sort of a one-to-one increase in two traits. So you'll see that there's a pretty big spectrum, again, of these genetic correlations that Angus accounts for. Things like weaning weight is about 50% correlated with dry matter intake. So an animal that weans off heavier is an animal that's likely going to eat more. So if you select for weaning weight, you're also going to select for increased maintenance requirements in individuals. Things like mature height here, you'll see has a fairly high correlation with weaning weight as well. All these carcass traits are fairly highly correlated with one another. So if you're selecting for carcass merit, you're going to increase a lot of these traits at once and hopefully in the right direction. So that's just a really brief introduction into genetic correlations. Not something we'll talk a whole lot about moving forward, but as we start to think about making these decisions in our own herds, these are the sort of things that we have to keep in mind. And so I'm going to switch gears a little bit here and move on from talking about heritabilities, genetic correlations, and really focus in on what we're doing when we're talking about genetic improvement. And I think that Justin, if you've heard him talk about his long game in the context of beef cattle production, I think that genetic improvement is the ultimate long game. These are decisions that we make one year, and they're going to have effects that go way into the future of our herd, right? So we have to have an eye on the future, and we have to be able to keep our eye on the progress that we hope that we're making. And I think that this is a good segue into talking about EPDs and some of the other genetic selection tools that we have available to us. So the big thing here that I'll use to tie into the last little section that I talked about is that relatives resemble each other. We know that's the case in complex traits. So if we want better offspring, if we want to improve the genetics of our herd, we have to select better parents. And the way that we do that is through genetic selection, focusing in just on the genetic component of these traits that we care about. And so some terms, just so we can be on the same page as I sort of move forward here. I've talked a lot about selection, and selection is the name of the game when it comes to genetics, right? What we're doing when we're using genetics in our herd is we're choosing parents for the next generation. And that's what selection is. And it happens on two fronts, right? So we do cow-based selection through the selection usually of replacement females, or maybe we're out buying females somewhere to be replacements in our herd. So that's going to be the cow-based selection. We're also doing bull selection. So we're going out, we're either picking out an AI sire, we're going to the auction, and we're purchasing a bull that's going to be a herd sire in our herd for multiple years. And when we think about selection, keep in mind that these decisions are ones that are going to have effects way down the line, right? As we talk about genetic inheritance, we're passing these chunks of DNA down to offspring. And in those offspring, if they're coming back into our herd as replacement females, that selection decision that you make here on a bull is going to have implications on your herd 10, 15, 20 years down the line, in both a good or a bad way, depending on if you made the right selection decision or not. So selection is again, the name of the game. And the thing that we ultimately want to select for is for an animal's true genetic merit. We want to pick the animals that are going to contribute the best genes to their offspring and that are going to perpetuate the goals that we've set in our herd that we want to achieve. But the thing about true genetic merit and the thing that keeps me employed is that this value is unknown, right? We can never know an individual's true genetic merit. So the thing that we have to do is use statistics, use these big pedigrees, use measurements of animals' phenotypes and all the relatives' phenotypes that we're able to measure to predict the genetic merit of an individual. And so when I talk about predicted genetic merit or estimated genetic merit, this is going to be a statistical estimate of that animal's true genetic merit. So since we'll never know this, the best we can do is take all the information that we have on an individual and try our best to predict this true genetic merit. And this predicted genetic merit is going to have some level of accuracy that comes along with it, right? So since we can never truly get right on the head of that animal's true genetic merit, we can predict it, but depending on how much information we have on that individual, that's going to affect how accurately this predicted genetic merit reflects the animal's true genetic merit. And then finally, as we talk about this long game of genetic selection, genetic improvement is ultimately the metric that we're concerned with, right? So as we look across traits, we want to see that steady improvement of the traits that we want to boost up in our population, and that's how we measure it, right? The change in true genetic merit over time is ultimately what we care about. And the way that we're able to do this is through a little tool that we call the breeder's equation. And so this is in most every animal breeding class textbook. This is the ultimate, right? The amount of genetic gain, or delta G, is this little Greek symbol in G. So that's the change in the animal, in the population's average genetics per year. So this is going to be on a yearly basis, right? We're not on a generational basis with cows. We want to make genetic progress every single year in our herd. And this is going to be dictated by these four things that are on the right side of our equation. And these are first, the accuracy of selection. So this R in BV stands for breeding value. So that's a breeding value is an animal's true genetic merit. So that's BV. And then this BV with the little hat on it, that's whatever we're using to represent this animal's true genetic merit. So this might be an EPD. This could be an animal's phenotype, because like we talked about with heritabilities, with heritabilities or with phenotypes, we can predict an animal's genetics to some variation depending on how heritable the trait is. But ultimately, this is what's going to dictate how accurately we're choosing the individuals that get to go on to the next generation through selection. The next thing that that plays into this is the intensity of selection. So how many replacement females are we keeping? How many bulls are we going out and buying? Are we being very, very strict in our selection? Are we only keeping a handful? And those selection decisions have a bigger effect when we have a more intense selection process. Genetic variation, I won't talk a lot about, but in order to make genetic progress, we have to have variation in the population on which to select on. If we have a completely inbred population, there's no way that we can improve it. So we have to keep some sort of genetic variation around. And then the last thing we'll talk about is generation interval, and I'll speak to that in just a second. But again, I think it's helpful to underline that this accuracy of selection, and we represent this as R, is how close is our selection metric, whether that's phenotype, whether that's a predicted breeding value or an EPD or whatever that might be, how close is that metric to the animal's actual genetic merit? And that's going to reflect, again, how accurately are we choosing the correct sire to be a parent in the next generation, the correct cow to get to stay on as a replacement female. And the last thing that we'll talk about as we move on here is generation interval. So this is an important one, right? How quickly are we advancing generations? Are we bringing new parents in? And this has a really big effect on traits that aren't able to be measured until later on in life. And we'll mention that in just a couple of slides. But this idea of identifying animals that are genetically superior sooner allows us to decrease this generation interval and make genetic progress faster. And so as we want to get on the same page, I want to also divide selection into two pieces, right? So the first being phenotypic selection. And so this is where we use some sort of a phenotype, some trait, our measurement of that trait on an individual to select the individual and whether they get to be parents in the next generation. And so this is what we've been doing for the last 10,000 years, right? Since cattle have been domesticated, we've been doing phenotypic selection on them. We know that we want bigger cattle. We know that we want cattle that made more milk. So we selected on the individuals whose phenotypes reflected those things that we cared about. But the thing about phenotypic selection is that results are sort of going to vary when we use it. And that's because, like we talked about, the accuracy of phenotypic selection is going to depend on how heritable that trait is. So if we're doing phenotypic selection on something like an individual's mature height, we're going to do pretty accurate phenotypic selection because that's a very, very highly heritable trait. For things like animal health, since that's such a lowly heritable trait, something like 5 to 10% maybe, our phenotypic selection is going to be very, very ineffective because the genetics play such a small part in the phenotype that's expressed. It's kind of like throwing darts at the wall with your eyes closed, right? You're just kind of hoping that you're catching some of that genetic variation, but it's such a small piece that phenotypic selection isn't very effective. And the other kicker here is that we have to wait for traits to be expressed. And this is especially important for things like fertility and especially cow longevity. So if we want to select a sire who's going to have daughters that stay around in the herd for a really long time, what we have to do is we have to choose that sire. We have to choose a whole bunch of sires that we want to test, right? We breed them to our cows. We wait for those cows to calve. Half of those are going to be females. We wait for those females to grow up to get bred, right? And then we have to wait for them to get bred multiple times before we can actually measure that longevity. So if we're doing phenotypic selection, we care about that bull's daughter's longevity. That's so far down the line that it's nearly impossible to do phenotypic selection on those long-term cow traits in particular. And now I'm going to talk most of today about genetic selection. So using predictions of an animal's genetic merit to do selection on that animal. And this is going to be in the form of EPDs, which I'll lay that definition out a little bit later in the presentation. But the important thing here is that we're able to remove the variation in that phenotype that's due to the animal's environment and focus on our predictions of that animal's genetic merit only when we're doing selection. And these also allow us to have predictions on an animal's genetics before that phenotype is expressed. So for things like fertility, maternal traits especially, it's very helpful to have these predictions early on in an animal's life when we're making selection decisions on it. And so we'll come back to this phenotype equals genotype plus environment slide. And I think it's helpful to break this out into the context of the phenotype is what we're getting paid for in our operations. So when you take a load of calves to the sale barn, you're getting paid for that weight, right? You're getting paid for that phenotype. But some of that is going to be due to the management and environment on your farm. And some of that is going to be due to the genetic potential of your animals, right? How good genetically are your bulls? How good genetically is your cow herd? And so when we're doing selection, when we're doing the selection that's going to be the most effective in increasing the herd's genetic merit over time, we want to focus in on this genetic component and not so much on the management or things that can't be contributed on to the next generation. In the context that I'll give here is if we're doing phenotypic selection, we could be selecting on this bull's appearance or his individual performance. Maybe he had a really, really big weaning weight, right? But some of that is going to be due to how a bull was raised. What sort of nutrition was he getting? Was that bull being creep fed? But the only thing that bull can contribute to his offspring is his genetics, right? So that bull can't pass on creep feeding to his offspring, but he sure as heck can contribute that genetic component of the traits that you care about in your herd. And I'll illustrate this one more way. I don't want to belabor this point, but I think it's really important to understand why doing genetic selection is so much more effective. And I'll do this in the context of phenotypic selection. We're trying to decide between these two bulls, right? We want to select the genetically superior bull that's going to give us more weaning weight and more yearling weight in our herd. So if we have these two bulls, bull A and bull B, you'll see that there's some pretty significant differences in these bulls' phenotypes. And if we knew that these bulls were raised in the same environment, we can be pretty confident that bull B is maybe the genetically superior of these two. But if we have these two animals and we have these two sets of phenotypes and we're trying to choose between them, and we know that bull A was raised in this really harsh environment, low nutrients, he wasn't getting a lot of help. His mother was maybe stressed nutrient wise as well. Whereas this bull B is out grazing that Middle Tennessee tall fescue. His mother was pouring the milk to him. It gets harder to disentangle whether these differences in phenotype are due to this bull's genetics, that he's actually genetically superior, or if they're just due to the fact that he was raised in a more favorable environment than this other bull. So as we think about phenotypic selection, we're not accounting for environmental differences. And that means that the selection that we're doing is always going to be less accurate than with a genetic prediction of some sort. And so the way that we want to do selection, right, is we want to pull out that environmental variation, the things that an animal can't pass down to their offspring. And we do that in the form of contemporary groups. So a contemporary group in the context of a genetic evaluation is a group of animals that are raised in a similar environment. They're given all the same nutrients. They're given the same sort of potential to reach their genetic potential, right? So animals that are managed in the same herd, the same year, the same season, getting the same resources. So we pull that variation out through contemporary groups. And what we're left with is the genetic component of that animal's phenotype. And that is what we're going to refer to as EPDs. And the last thing that I'll talk about here, just in the context of generation interval, is really underlining again the fact that having genetic predictions on an animal's genetic merit is the only way that we can do selection on some of these things. So say that we're interested in again, choosing between bull A and bull B, but we really want to make replacement females for our herd. Knowing that we want to do the selection, we have to wait a really long time to observe many of the things that we care about when we're selecting these bulls for maternal traits. So once we have that calf born, we have to go through heifer development until we maybe see what that fertility is as a heifer. Man, wouldn't it be nice to do selection on daughter fertility before we've ever had to put a daughter on the ground, before we have to breed these bulls to our cow herd? So heifer development, we can skip that step if we have an EPD for something like heifer pregnancy. We know that fertility right off the bat. That breeding and calving and that mature cow traits, right? And then if we start to think about things like cow longevity, again, this is going to be very central to a commercial cow-calf operations productivity and profitability, having cows that stick around in the herd for a long time. But if we can choose bulls at the very beginning, before we've even put a calf on the ground, that are going to be more likely to have daughters that stay in the herd for a long time, that's really, really valuable for us. So just another illustration of why it's important that we have these EPDs, because we don't have to wait for the actual phenotypes to be expressed in these daughters in order to make decisions between these two bulls and their abilities to make the sort of daughters that we want in our herd. And so I want to break down, I guess, why EPDs are useful. They're the next best thing to knowing genetic merit. We want to know that actual genetic merit, but they're going to be our best guess. They allow us to focus in on that genetic component of selection. So we're going to pull off that environmental variation. And they're useful also because we can do them in all sorts of traits, right? So if we can measure a phenotype on a large enough group of individuals, we can start to calculate EPDs on animals. So in the very beginning of EPD calculation, it was pretty bare bones, right? We had, maybe birth weight, maybe weaning weight, and maybe a mature weight EPD. But now Angus has got 24 different EPDs that they're reporting. They've got one coming out that has to do with early season hair shedding. So as a sort of proxy measure of how well an animal is adapted to heat stress, right? And again, if we can measure these on large groups of individuals, we can predict them in the form of an EPD and use that EPD to make better selection decisions, make quicker genetic progress. We can have these predictions early on, as hopefully I've driven that point home, and even for traits that aren't expressed later in life. And the other good thing about EPDs is that they're better than doing phenotypic selection very, very early on in an individual's life. But as we add information, they get more and more accurate. They better represent that animal's true genetic merit, so we can be more and more confident that by using an EPD, we're actually selecting on the animal's genetic merit. So just to lay out what EPDs are, they stand for expected progeny differences. And I think it's helpful to sort of break this out to understand how EPDs work and what they are. So they're predictions in the future. This is our sort of statistical definition of expected. So it's a prediction of the average or the mean in the future. And this future prediction is of an animal's progeny. And the difference component of this is EPDs allow us to compare the relative genetic merits of individuals to each other, right? So if we're looking just at the EPD of a single individual, not comparing it to anything, they're really kind of worthless to us. We always have to be making a comparison either to a breed average EPD or between selection candidates. So if we're deciding between bulls, we can only really interpret those EPDs if we're comparing them between the two animals. And typically these have to happen within populations. So an Angus EPD is not going to be directly comparable without some sort of an adjustment to, say, a Charolais or a Hereford EPD. So these are good for doing comparisons within populations. And what these look like in practice, I have a little example here where we're looking at a black bull and a gold bull. The black bull has a weaning weight EPD of 2. The gold bull has a weaning weight EPD of 22. What we would expect to see is that if we had a virtually unlimited number of offspring on these individuals, that maybe this black bull's average weaning weight, his calf crop's weaning weight is about 495 pounds. The gold bull's is about 515 pounds. And what this says, there's a 20-pound difference here. There's a 20-pound difference in those individuals' EPD. And when we look across all these animals, it's important to note that there's going to be variation around these averages, right? So not every single one of the gold bull's calves is going to be heavier than every single one of the black bull's calves. But what EPDs are telling us is that on average, there's going to be a 20-pound difference between the calf crop of a gold bull versus the calf crop of a black bull. So again, what we care about are these red lines, the high point of these bell-shaped curves that indicate the average. And again, we're always playing this game of averages, and that's what our selection decisions are hopefully doing. Isn't making every single individual better, but trying to push that average up compared to where we were the year before. And as we start to read and interpret EPDs, I think it can be a lot, right? A lot of these breed associations are throwing a lot of selection tools out, which is awesome. It's good to have more tools. We can make genetic progress on more traits that we care about in our herds, but it can be a lot to get our heads wrapped around. So this is an example from the American Simmental Association's website, where we're looking at an anonymous random bull. And this is a purebred Simmental bull. And these have predictions for things like birth weight, weaning weight, and yearling weight. These are going to be things that we can interpret in the context of pounds, right? So an animal whose birth weight is 2, and we're comparing that to another animal's, or 2.3, we're comparing that to another animal's birth weight EPD, which is 4.3. we would expect a 2-pound difference in the average calf crops of those individuals in regards to their birth weight. Same way we can interpret weaning weight, same with yearling weight. Things like average daily gain, how quickly an animal is putting pounds on once it's been weaned. Things like milk and maternal weaning weight. These are things that we care about further down the line when we're trying to select females for our operation. Stayability. This is a measure of an individual's likelihood that they're going to have daughters that remain in the herd up to 6 years of age, where they start to become profitable, so on and so forth. But I'm not gonna belabor this any more than is needed. But all these breed associations are going to report sort of trait definitions, how you can interpret these, and those are really helpful to read through as you start to dig through these EPD reports. The other thing I'll point out here is this little percentage line. So each one of these EPDs is going to have some sort of a percentile rank based on the rest of the breed. And what this is basically all of these EPDs are going to be on one of these bell-shaped curves. What this value is telling you down here is where this animal ranks compared to the rest of the herd, or the rest of the Simmental population. So for example, in this animal's milk EPD, this is saying that he's in the top 5% of the Simmental population for milk, which means that there's only 5% of animals in all of the Simmentals that have ever existed that have a better milk EPD than this individual. The same thing goes for all of these other traits. So that's a helpful point in way for you to place that animal in the context of the larger population and how good or bad they are relative to all the other animals in the population. And then you'll also see in a lot of these different breed associations, again, they'll be represented differently, but these things called accuracy, ACC, or possible change, which I'll talk about more in depth as we move forward here. These are measures of how well we think this EPD is predicting the animal's actual genetic merit and how confident we can be in using that EPD in place of the animal's true genetic merit. So with that, I'm going to ask another question. I think I maybe have one more later here. And my question is, what happens to the variability, so the distribution of calf phenotypes, as a sire's EPD accuracy increases?
Is this your last question? Did you say, Troy?
I think I might have one more.
Okay, I'm just making sure Courtney doesn't miss the opportunity to.
Ready to hear my joke?
Well, we didn't get one last week, so I just want to make sure we didn't miss it again this week.
Okay, I'll go ahead and tell it. And I kind of am doing a different one than I was originally going to do. Kind of goes with the genetics theme. So, okay, so what happened when the farmer crossed a chili pepper, a shovel, and a terrier?
Okay, so let me make sure I've got this right. I'm thinking about other breed types as I'm typing answers to questions over here. I don't want to get this mixed up. So a chili pepper, a shovel, and what was the third?
A terrier.
A terrier. So this would be like a chili pepper, shovel, F1, and the third breed cross, breed that F1 back to a terrier.
Yep.
Is that what we're talking about? Okay. I think with that amount of information, I don't have an answer.
Okay, he got a hot diggity dog.
Hot diggity dog. That's a good one.
Yeah, that's outstanding, I guess.
Best one yet.
Yeah.
All right, I'm going to share results with you.
All right. So the overall answer here was that about 30% said that variation increases, 60% said that variation decreases, and 6% said that variation stays the same. And this is a thing that I hadn't really thought about until very recently, or put it into words. But when we're looking at an individual's accuracy, and I'll get to this in just a second, the actual distribution of those calf phenotypes is not going to change as we add more information. The EPD's accuracy is only going to tell us information about this mean and how confident that we are that that mean is the animal's actual genetic merit. There's still going to be some sort of randomness in this distribution of calf phenotypes. If you breed to a bull that's 99% accurate, you're still going to get some calves that are big at birth, some that are really small at birth, and a lot that are in the middle, right? That distribution isn't going to change, but our confidence in the fact that that prediction is representing that animal's true genetic merit is the only thing that'll change there. So again, this idea of accuracy, where the more accurate our predictions are, the more confident we are in that EPD representing the animal's true genetic merit. So for young sires that don't have any offspring information in a genetic evaluation, these are going to have low accuracy, which means that these EPDs, this estimate of the mean of this distribution, can really shift quite a bit as we add more information in. So in the context of our example here, these big possible changes that we have surrounding the EPDs, the predictions, these can change quite a bit if either of these bulls got more information added into the evaluation, and they could possibly re-rank because there's so much possible change that can occur because they're low accuracy animals with no additional information than their parents' genetic averages. But as we add more offspring, the confidence in these predictions gets much higher, and the possible change shrinks down. So there's less shifting around that these EPDs can do, our estimates of these means, because we've got so much information after these bulls have had a number of calf crops. And so again, this goes back to the poll question. The increasing EPD accuracy doesn't change the distribution of calf phenotypes, right? The only thing that an accuracy is telling us is how confident we are that this red bar exists here, right? It's not going to do anything to the fact that this gold bull is going to have some really, really small calves, some really, really big calves, and a whole lot of calves in the middle. So those distributions stay the same. So even if you've got a 99% accurate AI sire, you might still see some variation in that calf crop. Because again, we're not changing the genetics at all, just our confidence in the prediction of that animal's true genetic merit. And so again, higher accuracy, less possible change. It's indicative of our confidence. So how well are we representing a true genetic merit? And the other thing that I'll throw out here is that accuracies are difficult to calculate. The genetics community can't really agree on how we want to calculate accuracies. So there's lots of different measures of accuracy. And these are going to differ across breeds. So making a comparison between a 90% accurate Angus AI sire and a 90% accurate Simmental AI sire, because those are different evaluations, we can't make those direct comparisons with accuracy. Zipping back to our EPD reports, and I'm coming up on time here, and I want to leave plenty of time for questions. So I might move through a couple of these a little bit quicker because I want to get to a couple points here at the end. But when we look at I really like how Simmental reports their accuracies, both as an accuracy. We call this a BIF accuracy. So the Beef Improvement Federation has agreed on how we want to calculate accuracies. And that's what is reported here. But I think that BIF accuracies are hard because they don't give us a whole lot of context in a vacuum, right? So what does a 0.56 accuracy mean compared to a 0.35 accuracy compared to a 0.75 accuracy? So I've really enjoyed how Simmental has started adding in this possible change that's associated with an EPD's accuracy. And the way we can interpret this is, you see it's a plus or minus and then some sort of a value. So what this is saying is that we can expect within reason that this birth weight EPD could change either up 1.32 or down 1.32 as we add more information into this genetic evaluation. So as this bull becomes more proven, say he's an AI sire, we're getting lots and lots of offspring records back on this animal, we would see that accuracy go up. We'd see that possible change associated with the EPD shrink down pretty small. And here's a good example of this as we compare across a young calf who doesn't have any information except for its parent average EPDs. That possible change is really big. That birth weight could end up in the negatives, or it could end up all the way up close to 4.5, right? So that could do a lot of shifting around as we had more information. This moderate accuracy young bull that we had on the previous slide, you can see higher BIF accuracy and also a smaller possible change associated with that EPD. But for a very high accuracy proven AI sire, you'll see that possible change shrinks down very, very small. So in this case, we're very confident that this EPD is quite close to that animal's true genetic merit, and it's not likely to shift around as we add more data into the database here. And so this leaves me with my last and final question as we sort of dig into why, what are we doing with accuracy, right? What is adding additional information? And so my question here is I guess more of a personal one. Do you have a sibling? And are you better looking than your sibling? And the possible answers here are yes and yes, yes and no, or no if you don't have a sibling. And this is brought to you by some of our favorite Manning siblings here in the state of Tennessee. So I don't know. I have a pretty good idea how this one is going to come out because I've asked this at a number of in-person events, and everybody seems to think that they're better looking than their little brother, including myself. But Courtney, what about you? Do you have siblings?
I have 3 older sisters and a little brother, and I'm gonna have to say yes, 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 yes.
Yes. That works. Same with me here. You guys want another joke while we're waiting?
You got one?
I got one. I'll see if Justin can get this one. Justin, why do Swedish warships have barcodes on them?
I can't even begin to give a good answer to that.
It's so that when they return to port, they can scan the Navy in.
Oh, wow. That's actually pretty good.
That's pretty good. Yeah.
Yeah. Have you seen those videos on dad jokes where they try not to laugh at each other's?
Yep.
I'm trying not to laugh, but that's a really good joke.
All right. You're free to distribute that as you see fit.
Oh, I will.
So it turns out that 12% of you guys don't have siblings. I'm kind of surprised that 19% of you do have siblings and don't think that you're better looking than them. But 69% of the audience tonight has a sibling and knows that they're better looking. So my purpose for this is that a lot of what we're doing in genetics is trying to disentangle this resemblance between relatives. And we know that the same thing happens with cattle, right? So we know that even in full sibling families, and we have lots of these in beef cattle, we can have animals that are from the same sire, the same dam, but there's going to be quite a bit of difference in not only their phenotypic differences, but also in their genetics, right? So we could have these 3 bulls who are flush mates, right? And they might even look very similar phenotypically, but as we get more and more accurate EPDs, we see that this individual A is genetically superior to his 2 full siblings, bulls B and C. And the reason that we know this, right, and the reason that this happens is that we're going to inherit 50% of our DNA from each parent, no matter what, right? That's sort of a given, whether you're a cow, you're a dog, you're a human, right? You're going to get 50% of your DNA from mom, 50% from dad. And you'll see that the same thing happens here, right? You got each of these bulls has chunks of their DNA from mom and from dad. But the issue is that we're inheriting a different 50% from each parent if we have siblings, right? So the chunks of this animal's DNA that he got from dad are different from this animal's chunks that he got from his dad, and in the same with his other full brother here. And the issue that arises, right, is that if we're not inheriting the exact same DNA as our siblings, there's chances that we could get better chunks of DNA. There's chances we could get worse chunks of DNA. And really the whole of genetics is concerned with figuring out on a population scale, so not just focused in on these individual full siblings, but trying to figure out these, knowing that our pedigree relationship doesn't equal our DNA relationship, right? Even though we're 25% on average related to each grandparent, you'll see that some of these bulls have bigger chunks of DNA from certain grandparents, and trying to disentangle that and figure out which chunks of DNA an individual got, because ultimately that's what's going to represent their true genetic merit, is if we know what favorable chunks of DNA they got versus what unfavorable chunks of DNA they got. And so as we look at an animal's genetic merit, we know that it's going to be some combination of half of the sire's genetic merit, half of the dam's genetic merit, again, because they're only passing down half of their chromosomes to the offspring. But then and so that's what's going to account for the resemblance that we see between relatives. Because these animals do share quite a bit of their DNA with each other, we're going to see resemblances. but there's also going to be this randomness that gets thrown in. And in geneticists, we like to call this Mendelian sampling. And you can think about this as just the random sampling of genes. And what EPDs are concerned with doing, and the increasing accuracy of EPDs, is concerned with figuring out what exactly this Mendelian sampling term is, because that allows us, once we have a better estimate of what that is, that allows us to predict the animal's actual genetic merit with a lot more confidence. And just a quick example here of Mendelian sampling and how it can play out just on the inheritance of DNA between two siblings from their sire. So this is a sire's DNA, and each one of these spots is a place in the genome that is going to affect some trait, some random trait that we care about. And each plus is +1, a minus is -1. So if we sum across all of these, the sire's genetic merit is -4. But when we look at these two full siblings, depending on which chunks of the sire's DNA, as you can see, Bull A here ends up +11 because he inherited probably the two best stretches of his sire's DNA. So these chunks of DNA will swap with each other, and we can have basically an infinite number of combinations that animals can inherit. So this guy, he got the good shake out of this DNA swapping, because he got this whole big chunk with a whole bunch of pluses on the red sire chromosome. And then it swapped right here with the yellow chromosome. So we got a handful of pluses down here as well. Whereas his brother really got the short end of the stick and ends up -15. So the same sire DNA that we're choosing from, but just depending on which chunks they inherit, can really affect the genetic merit of these individuals, especially when we look across the genome and we sum across the billions of base pairs and the millions of DNA differences that we know come to play in these complex traits. So that's just a really brief illustration, but hopefully it helps us understand a little bit about how we can see this variation between siblings, how some of us can be, incredibly handsome with our less handsome little brothers, right? And it all comes down to this fact of Mendelian sampling. And Mendelian sampling plays into our predictions of true genetic merit, because without that information, without an accurate prediction of Mendelian sampling, our true genetic merit here in the middle of the bullseye, we can get pretty close to around it. But once we add all this information, we can start to say we have a sire and we're pretty confident that he's got a good weaning weight EPD, right? We're pretty confident, but without the information of a bunch of above average weaning weight calves, we're not able to say that we're super confident in that prediction of his genetic merit. And there's two ways that we can come at this, how we can start to identify the genetic differences between full siblings. The first is to have a whole bunch of calves. So these come in the form of progeny records. So we're always going to increase the accuracy of an EPD if we add more progeny to the genetic evaluation. And since we started calculating EPDs, this is the way that we've gotten more confident and better resolve those differences in the DNA chunks that these animals inherited through pedigrees and through traditional EPD calculation. But more recently, we've been able to utilize genomics and start actually tracking the chunks of DNA that individuals inherit. And we can assign values to those chunks of DNA that individuals inherit and predict, just based off of an individual's DNA that we get through a genomic test, what that animal's genetic merit is. And so genomically enhanced EPDs are just the next step to increasing EPD accuracy. And they allow us to do that earlier on in an animal's life before they've had any calves. And I hope I can illustrate this without taking up too much time. So traditionally, the way that we've calculated EPDs is we have these big databases that are made up of a pedigree of hundreds of thousands or millions of animals. And if we're looking at an EPD for an individual animal, we have all these relationships that we guess how related they are to all of these other individuals in the pedigree. So we know they're going to be 50% related to their mom and dad and their full siblings. We also know they'll be a quarter related to their first cousins, and so on and so forth, right? But so we have this pedigree information. We have that animal's performance. So how well did their phenotype get expressed? They have big weaning weight, a little weaning weight, so on and so forth. And then we add information from progeny that help us increase the confidence that EPD is representative of the animal's genetic merit. The only thing that changes as we start doing genomically enhanced EPDs is that instead of just guessing on those animals' relationships with others, we're actually looking at the DNA and saying, how genomically related is this animal to this other animal, right? These guys might be first cousins, but he's actually 45% related instead of 25% related to this other individual. And when we do this on a grand population scale, we can leverage all of the other performance records on these individuals in the pedigree, and we can more effectively do that using genomics. And the result is a more accurate prediction of that animal's genetic merit. So I think the most helpful way to think about genomic tests is in the context of progeny equivalence. So what a progeny equivalent is it's saying how many calves records will we have to have enter the genetic evaluation in order to see the same increase in EPD accuracy that we get through a genomic test. So this is a table taken from the American Angus Association, looking across a variety of the traits that they're reporting, but saying how many individual animal records is a genomic test worth in one of these individuals. And for things like calving ease, weaning weight, you see that this is upwards of 20 to 30 records that a genomic test is worth. And even for some of these other traits that don't have a ton of records in the genetic evaluation, you're still getting 10 animals worth of information just by doing a genomic test. So what this means in the place that this comes into big play in the beef industry is that by doing a genomic test, we can go out and we can buy a yearling or a 2-year-old bull who doesn't have a bunch of information. He doesn't have that sort of progeny information that's going to increase the accuracy of his EPD, but we can go out and get a genomic test and we can get almost a calf crop's worth of information on that animal just based on his genomic profile. So this is going to allow us to be more confident when we're selecting these young sires, these virgin bulls who we haven't had a calf crop out of, that the EPDs that are being reported on them are closer to their actual genetic merit, that we don't have to have that dystocia train wreck of a calving season, right? We can be pretty confident that this bull, before he's ever put a calf on the ground, is going to be calving ease. And same goes for these maternal traits. Before he makes daughters, we can be even more confident that prediction is close to his true genetic merit. And so the easiest way to use genomics is to always buy a bull that has genomically enhanced EPDs. So any AI sire, if you're using artificial insemination, those bulls are always going to have genomically enhanced EPDs. But for bulls that you're going out and buying, making sure that the producer that you're purchasing them from, the seed stock operation, is doing genomic testing is really going to help you be more confident that those bulls are what you think they are based on the EPDs that get reported. And so I think I've used about an hour of your time up, and I want to leave plenty of time for discussion and for questions, but I want to leave you with just a few things here. The first is, I think, a really exceptional set of resources that myself and some of the other genetic and genomics beef cattle extension specialists from across the country have put together through this initiative called eBeef. So there's tons and tons of fact sheets here for all things from coat color genetics up to selection indexes to EPDs to reporting phenotypes. Literally everything in between there's probably a fact sheet on the eBeef website. So as you come up with questions, I love to point people at these. They're easy reading, they're short, and I think they're really, really helpful for the beginning cattleman getting a grasp on things like genomic testing and genetics and how that factors into your herd. So give those a look if you have a chance. And my big takeaways for tonight is that improving genetics is going to be essential for the longevity of the beef industry, right? We want to stay sustainable. We want to pass on this tradition to our kids, our grandkids. And I think that genetic improvement is still going to keep playing a big part in that. We want to make the animals that are going to make the beef industry more profitable for us so we can keep this thing going. And most economically relevant traits, so the traits that are going to make us money, are going to be complex. So they're going to have these very highly polygenic, lots of genes playing into the expression of these traits with differing levels of genetic influence, right? So from these very high heritability traits like stature, mature size, all the way down to the lowly heritable traits, like things such as fertility, animal health, and understanding that regardless of the heritability of these traits, genetic selection is going to be more effective than phenotypic selection, because it allows us to focus in just on the genetic component of that. Doing phenotypic selection on an individual's fertility isn't going to be effective because such a small proportion of that is controlled by genetics. But if we have an EPD for that, we can be much more focused on selecting just the genetic component of that, and not inadvertently selecting on those environmental factors that come into play. And then finally, EPDs and genomics are going to allow us to make more effective selection decisions, focusing in on that animal's genetics, just what they can pass on to their offspring. It's going to reduce risk, and it's going to increase that rate of genetic gain, that delta G that we care about over the long term as we're trying to select better individuals that are going to go on to make the beef industry more and more sustainable. So with that, I'm going to wrap up. I'll leave you here with my contact information, and I tell everybody this: I'm a resource for the state of Tennessee. So if you have questions, don't hesitate to shoot me an email, give me a call on my office phone, tweet at me, whatever works. I'm more than happy to be a resource to y'all with any questions that come up. But with that, I'll let Justin sort of MC this discussion and see if he's got anything for me. So thanks again for tuning in, and I appreciate everybody's patience and being here for Master Beef.
That's great, Troy. And I especially appreciate you leaving some time here, next 20 minutes or so, to have some discussion, ask some questions. There have been a ton of really good questions come in. All these questions have been great. So I'm going to throw one to you as one of the last questions we got, but I think it'll be one that you like to answer.
Yeah.
So the question, kind of paraphrasing here because I don't have it up right in front of me, but it's what do you think about using value indexes?
Oh man, that's that'll be my next talk here for Master Beef will probably be on selection indexes. I think that selection indexes, I didn't go into any detail here because we were trying to go back to the basics. But I think that selection indexes are an incredible tool for the commercial cow-calf producer. And for those on the call who maybe aren't so familiar with what indexes are, instead of doing selection just based on one EPD, a value index is a bunch of economics and genetics people put their heads together, and they come up with this multi-trait index that allows you to account for some of those genetic correlations, both good and bad. But most importantly, it allows you to put a relative economic weight on multiple EPDs and select on them in aggregate, right? So if you're a commercial cow-calf producer and you're selling all your calves at weaning, and you're keeping replacement females, there are lots of different traits that are going to come into play with how profitable your animals are going to be. And so an economic selection index allows you to put heavy weights on the things that are going to make you money. So things like cow longevity in that case, calf weaning weight, calving ease, those are going to get relative economic weights based on the dollars that those are going to contribute to your profitability per unit increase of an EPD. We add all those up, those EPDs weighted by their relative economic weights. What we're left with is a single value that allows us to compare individuals to each other based on how profitable they'll be under these generic production scenarios, right? And again, I think that value indexes are a fantastic tool. Lots of thought that goes into them, and they get us away from this idea of doing single trait selection, which we can run into some roadblocks sometimes, right? If we're just selecting for weaning weight, we could miss that thing that contributes to our profitability in a big way, in the form of maternal traits, in the form of calving ease, in the form of making big, heavy, mature cows. So if that didn't tell you enough, I love economic selection indexes, and I think that they're an awesome tool that we'll have to give some more lip service to in future Master Beef. But I think they're an awesome tool, and I can't encourage you to dig into those at each breed association and start utilizing those in selection decisions in your herd.
Yeah, and definitely I'm on board with that completely. There's it would be great to take a session like this and parlay directly into just examples of how to, if I'm going to a bull sale, how do I use these? And I think that's where we go from here. There's a couple of things. We'll have a panel discussion. I think will be the last session we have on this webinar series, and maybe we'll be able to get into it more there. But also, we're developing other trainings and have other trainings in place too that your agent or us can bring to you about, now that I know these basics that Dr. Rowan's presented to you this evening, how do I use those to sit down with a bull sale catalog and pick what bull I want to bid on? So that's kind of the next step of this. If we tried to cover all that here, we'd be hours and hours, maybe a full day webinar series all at one time, but we'll do it in bites and chunks. So definitely indexes are a big part of that for me if I'm trying to help somebody find one. I'm going to read kind of a scenario here that one of our attendees wrote in, and I think this will give us a place to maybe answer or talk about some other questions that have come in too. So they write, we currently have 75 mama cows. Original goal is our goal is to cut this number in half and maximize our land in order to give the best opportunity to make the most money with a smaller herd. And I like that idea, giving some flexibility, not maximum capacity stocking rate. So that's part of the scenario here. We currently have a mixture of Angus, not registered, so commercial Angus, commercial Hereford, and Romanola. Based on your knowledge, would you suggest that we sell our current herd and begin to build a quality registered herd? We are in our 50s and look forward to farming for 20 more years. So basically, to me, it kind of comes down, going to try to optimize their land-based use instead of maximize.
Yep.
And I like that concept of, I'll just kind of throw a little aside here. I like being able to do that. And, you have your calf crop. If you have a bunch of grass when you wean your calves, you can background them for a while and not get in a situation where you have to sell a bunch of cows when you have some drought and then buy back and you're constantly going back and forth like that. I call it kind of a flex scenario that you have the flex in your calf crop instead of constantly changing your cow herd. But maybe the direct question to you, Dr. Rowan, out of this would be, if somebody's going to have a smaller type herd, should they go purebred seed stock production, commercial production? Just generally, what's your take on that from a genetic management standpoint?
Yeah, and when I give talks that are more focused on sire selection exclusively, I always start off talking about breeding goals because I think it's easy for us to jump right into to EPDs or into selection indexes or whatever. But I think that being really intentional, and I think that's a great question because that tells me that you're being very intentional about the breeding decisions that you're about to make, because too often we're at a bull sale, we're making selection decisions and we'll figure it out later. Right. So I really like that forward thinking approach. And I think it really just is going to depend, right? How hands-on do you want to be? How risk tolerant are you? And maybe these are questions for Charlie Martinez, our extension economist guy. But really, I think it just depends. And I think there's lots of ways that you can have a profitable herd just running commercial animals, right? You don't have to get into being a big seed stock player. You're going to have more money up front if you're trying to play the seed stock game. I think there's a lot of value in trying to find a specialty market maybe for your animals, right? With that sort of size, you pare back and you can find a way to maybe do freezer beef or selling. Being intentional about those cows that you keep around, and going forward with a plan like that, some way to add some value to those animals, aside from just sort of, like you said, trying to maximize and sell a set of calves at weaning and hope that everything goes all right. I think there's lots of ways that you can add value to small numbers. Both if you go the seed stock route, you're again a bigger upfront cost if you're trying to build from basically ground floor there. Whereas I think that with a base of Hereford and Angus animals, right, you can start to make some really nice commercial replacement females. I love a black baldy. You guys will hear me talk about crossbreeding and heterosis a lot. But I think that's a good base for you to jump off and just do some more, again, targeted and focused commercial cow-calf production. whether you're marketing those animals or retaining ownership or like Justin said, just building in some flexibility to background your own calves. I think that there's a lot of different routes you can go there. And like any good extension professional, I'm gonna say it depends, right? But we're more than happy as you guys specifically, or anybody, as you're faced with these decisions. We're happy to talk about these in person, on the phone, via email, and give support where we can lend it, right? We each have a little bit different expertise, and I think it's going to depend on every individual case. But again, we're happy to give those more specific consultations moving forward, and work with your extension agent to help you make that decision. But in the context of the broader webinar, I guess I'm gonna leave it at depends.
Yeah. And that's kind of a good thing to bring up, maybe a little aside from genetics, but we often do have to give that answer. And as I'm typing answers to questions coming in, we love to try to be very direct, and I'd love to give you an ABC answer, and I know Troy would too, but it's just not that easy, right? That's the difficult thing about what we do. It's not like we're working in factories and can cut and paste in exact replicates into something like that. So, oftentimes we do need more information on your specific scenario, but we can get fundamental kind of things like knowing that if you are going commercial and you're running a commercial cow herd to improve reproduction, heterosis is a great way and very effective tool to use to improve reproductive performance. So we had a lot of questions. I'm kind of making a transition here. I had several questions about heterosis and how to manage and use that. Some of it was what's the best breeds to cross. So it's going to be an it depends thing, right? It's going to go back to what you mentioned about setting your breeding goals. It has a lot to do with where you are. Even the environment from Mountain City to near Memphis is going to be totally different enough to make that different answers, very different answers. So some more I think that we can give direct, or that you can give direct answers to, would be how do you maximize how do you to maintain that heterosis in a commercial herd without letting it get diluted out, and maybe even some more basic stuff like, well, what's an F1, and then where do you go from there after you make an F1 female?
Yeah, no, and I'm glad you brought this up. This is my other, economic selection indexes and heterosis are my two big talking points. And I semi left heterosis out because I probably talk about it too much, but I don't think I can. So I'm glad this got brought up, and I'm glad that this is on everybody's minds, because I think that as an industry, doing crossbreeding effectively is one of the big places that we can still make a lot of improvement. We don't have to bring in some crazy new tool, right? But utilizing crossbreeding effectively, I think, is a really, really fantastic tool for a number of reasons, right? The big one is heterosis, right? We're seeing that increased performance in that F1, that first generation cross offspring. And the thing that Justin mentioned, this sort of off the cuff, but as we're thinking about the heritabilities of certain traits, you always hear me talk about, fertility, animal health. These things are all sort of lowly heritable traits, but these lowly heritable traits are where we see the biggest influence of heterosis on them. So for things like fertility, cow longevity, animal health, they're lowly heritable, but the effect that we see in these F1, these first generation cross individuals is way bigger for lowly heritable traits than for highly heritable traits. So if you're a commercial producer who wants to see genetic improvement, or I guess just an improvement, not necessarily genetic in the context of increasing genetics over time, but you want to improve fertility, a very easy way to do that is introducing crossbreeding, right? And there's lots of ways to do it. We can go as easy as bringing in a terminal cross bull to put on our commercial cows. Justin said we won't make any recommendations about breeds, but as a good Charolais breeder, I'll never refuse a chance to say that a good old Charolais bull on some commercial Angus females will make a heck of a set of terminal cross calves. But the same goes for a number of other breeds, right? We can figure out ways to do this, but like Justin said, this is all going to depend on our breeding goals. If we're trying to make replacement females, that Hereford Angus cross is very popular. If we're in an environment that's not friendly to cattle, we get down further south. I think that introducing in some of these tropical composite breeds, right? So a Brangus or something along those lines, a little bit of ear wouldn't necessarily hurt anything in a lot of places in the Southeast here. So there's lots of ways you can go. Again, from as simple as bringing a terminal cross bull in to having a multi-breed rotation and everywhere in between. And a really good resource to read more about heterosis that I go back to, sort of a very good applied definition of these crossbreeding programs. You can find on that link up above, the eBeef fact sheet on crossbreeding is very, very helpful and can hopefully shoot you down some of these other paths. But too long didn't read. Heterosis is great, and if you're a commercial breeder, you should be using crossbreeding because you're leaving pounds on the table if you're not. So that's my big takeaway, and I'm glad that heterosis got brought up. I didn't have to go a whole webinar series without talking about heterosis.
Yeah, and you probably had somewhere in your subconscious knowing that even if you didn't mention it explicitly, I was going to bring it up as a repro guy.
Yeah, exactly.
But luckily, the questions did come in from the attendees, so I'm glad people are thinking about that and asking about it. And I don't want to beat that to death because I know we have a couple other good questions here to answer. But I always say that if you look at other protein, animal protein sources, any other animal protein source, they all make an art out of using heterosis. You started with poultry production. I mean, that's just, I don't want to get too hyperbolic here, but exquisite the way that they use heterosis in breeding, poultry and poultry production to make broilers. And they're more efficient, partly because of the animal, but also partly because they are very aggressive with the way they use genetic tools like heterosis. So anyway, I can get as carried away with talking about it as anybody else. So I'm glad we're on the same page there.
Sure.
You'd mentioned some about heterosis and talked about some kind of single gene traits a little bit, I think. So I'm changing up a little bit to talk more about basic genetics, I guess. I'm just going to read this question as is, but there are some others that ask it in different ways. And I don't even know how to begin to answer some of this with composite breeds and how these single trait or simple trait genetically controlled traits are. But so the question is, since horns and color are simple traits, if you breed a homozygous polled, homozygous black Limousin to a black Angus cow with a bull, or will the offspring be homozygous black and polled?
Yeah. If you're breeding a homozygous polled Limousin bull, homozygous black, homozygous polled Limousin bull to a homozygous black, homozygous polled, you assume in Angus that there's not going to be any horns and no color in Angus. You're always going to get solid black calves there. So in the context of dominant versus recessive, the horned trait is always going to be recessive. So if you have a homozygous polled bull, you're never going to get a horned calf out of him. Okay. And the same thing goes for black, right? Black is dominant, except for a corner case that we were talking about before the webinar started. But generally, black is always going to be dominant to these other traits. Coat color gets a little trickier because there's a number of different chunks of DNA and genes that are involved in that whole thing. And simple traits aren't exactly my forte. But as far as black and polled go, those are sort of the ones that you can be pretty confident that if you've got a homozygous black, homozygous polled, no matter what you're putting that Limousin bull on, you're going to get black and polled calves.
And sometimes maybe I read a little too much into these questions because I think, the person that asked that question might have had a situation where they thought they were breeding that way and got a little bit of surprise. And sometimes that happens. But, for instance, I've seen a situation like that where they, I mean, know for certain that the offspring should come out and not be horned, but it had scurs.
Yeah.
And the situation I'm describing, I'm trying not to get too specific about this, but it should have been it was a purebred situation where that animal shouldn't have had any kind of scur or indication of horn genetics somewhere behind it. But sometimes you get surprises, right?
Yeah, no, and that's another thing that as we think about the big pedigrees that all these genetic evaluations are built on, and the same for these things like the simple traits that we're reporting, right? A messed up, sire 2 generations back, that sort of thing can trickle down, right? Oh, he was homozygous polled for sure, but he was actually heterozygous polled, and you've got that recessive allele floating around that can show up in a couple generations. So a big reason why these breed associations care a lot about getting these pedigrees right, because the effects that they have across the board on EPD accuracy, on things like polled and coat color, all of those are really, really impactful. That pedigree has to be just right and as close to reality as possible, or you can run into these surprises that you think the neighborhood bull got in, but it's actually just a pedigree error.
Yeah. And that's a good way to say it, and kind of the way I think about it sometimes. If you run into something that doesn't play by the textbook, instead of blaming the textbook, a lot of times it's better to go look at the data behind it to make sure we know exactly what was in there.
Right.
So I'm going to throw one last question at you. I do want to say, though, it happened really quickly to me that we're at the 7 o'clock central hour. So if folks need to fall off, go ahead and do so. If you got other commitments you need to get on to, we want to be respectful of your time. But I am going to ask Dr. Rowan one last question here to finish up. If I wasn't able to get to the question that you typed in to discuss it here, please feel free to reach out to us. That's why we're here. Dr. Rowan's already mentioned that a couple of times. He has information up here. Reach out to your county agent that's facilitating this for you, your master beef producer certification course. They'll be glad to help you. We've got a lot of really good agents across the state that know a lot about genetics and genomics and genetic selection. So the last one I'm going to give you, Troy, is kind of another one that I know has been a hot topic, seems like, for whatever reason. I'm not certain why this is taking hold again, but inbreeding and line breeding. So the question as it's written is, we hear so much about inbreeding. What is your take on bull breeding, breeding a bull back to daughters and, that mothers and that kind of thing? So I know you and I have talked about, you get some questions. I guess maybe people see popular press articles about line breeding. Just want to give you an opportunity to address that and the nuances of it.
Yeah, I think that there is a lot of nuance there. I've also the quote that I remember from my childhood was it's line breeding when it works, it's inbreeding when it doesn't. But I think that there's a place for inbreeding or a place for line breeding, right? And that's when if you're a commercial producer, you shouldn't be line breeding at all, right? There's really no reason to be coming back onto dams with their, with a son or with a half brother to their sire or whatever, right? There's bringing in new genetics is easy enough in a commercial operation. It's almost never necessary to do anything of the sort. It might be an okay context in a seed stock, if you're a seed stock context, where you're selecting very hard and you're making genetic progress and you're so far ahead of the rest of the population that it makes more sense to risk those effects of inbreeding than to bring in outside genetics, right? You're going to sacrifice the genetic gain that you're getting by bringing in outside individuals. But the cases where that's effective and useful in today's world are very, very few and far between, right? So It's easy enough to, if you're a big seed stock producer, you're making crazy genetic progress, to bring in outside genetics, some sort of an outcross, so that you're not going to have to deal with all the things that come along with inbreeding, which I like to think about inbreeding as the exact opposite of heterosis, right? Heterosis is adding in all this genetic variation. Inbreeding is sort of pigeonholing you into this genetic variation, into what genetic variation is there that you're starting with. And again, it's great if you're getting all the favorable DNA, but the stuff that comes along with it, the genetic defects, the lethal haplotypes, so sort of early embryonic loss that comes from these incompatibilities when you have homozygosity all across the genome. There's just lots of baggage that comes along with line breeding, and so the contexts where it makes a ton of sense are really, really shrinking in today's world with the access to artificial insemination and all of the other tools that we have to put good genetics on good genetics, and not have to just pull from the same genetic pool.
Yeah.
So that was my long and circuitous explanation of why you probably don't need to be line breeding.
Yeah. And that's a very safe assumption. I think I've met one person that I've felt confident did it well, and they had thousands of animals and were willing to take some losses with it for the very specific reason they were trying to do it. So it's
Right.
very rarely something that most people would need to use. And I like the way you said it's the opposite of heterosis.
Yep.
Somebody typed in another good phrase, said, in your herd, it's line breeding. In your neighbor's herd, it's inbreeding.
Yes, sir. Yes, sir. That's a good one.
That's a good, and the thing that really makes it clear in my mind is back before we had genomic testing for defects, the way they would test for it is to breed sires back to their daughters to see if they popped a defect. And so if you can make them intentionally by doing that, then it's probably not a good idea to toy with it, right?
Yep. Absolutely. So.
But Troy, I think that kind of brings us to the end of our time here. So many other good questions and good discussion to have. With that said, I really look forward to our panel discussion at the end of this series. That'll be fun to get some of this discussion going again and talk about how all this interplays. We've kind of talked about reproduction and genetics and these other things. That'll be fun. I'm looking forward to that part of it, and just everybody talking about it together and how they all mesh. So. Troy, I really appreciate your time this evening. I know all the producers do, and I'm saying this like we're not, you're just as much part of this Master Beef deal as any of the rest of us. So just glad you're here with us, and glad you're part of the extension team and UT Animal Science, and look forward to many more years of doing Master Beef producer programs with you. So thanks, man.
You betcha. All right. Yeah, we covered a lot of ground, but I appreciate everybody that stuck on until later in the evening here. So have a good one, everybody, and we'll sign off for now.
Courtney, anything else we need to cover?
All good. Whenever I hit end, the survey will pop up in your web browser, but if you don't see it initially, you'll get an email with it tomorrow night.
Okay.
Bye.
Thanks.